Lecture 1 had dispersion forces. We had dipole-dipole, hydrogen bonding, and ionic. Now the second half of Lecture 1 focused on the basics of organic chemistry. We learned how to name organic chemicals, and we learned their basic properties. Now we focused on hydrocarbons. We focused on alkanes. Now if we step that up, we can add something called functional groups. Now I want you to think of a kid going swimming. Now if that kid doesn't know how to swim, he's going to have a few things to help him out. We'll draw our kid down here. Let's get our pen out. We'll doodle some. Now, here's a picture of our little swimmer. Got a little stick figure here. Now, some things that might help him swim. We've got inflatable arm swimmies we can put on him. We also have an inner tube that we could put around his waist. We can also put a snorkel, and we can put goggles. Now what we've done is we've taken just a regular human who's not capable of breathing underwater, and when we add the snorkel, we add the capability to be able to breathe while your face is underwater. Normally, with our Joe average human on the left here, you get water in your eyes when you're underwater. We add the goggles, that's no longer a problem. And finally, when we add the arm swimmies, we've added flotation devices. Where normally this human might have problem floating, he can now float in the water comfortably because of these flotation devices. We've added functional additions to this human. We've added the flotation devices, we've added the snorkel and the goggles. Each piece had a purpose. One for floating, one for breathing underwater. We can think of the same way if we have a skeletal organic structure that's just a hydrocarbon, and then we can add something to it. We can add a group. Might be an OH group. I can add another OH group over here. If we just had a plain hydrocarbon, hydrocarbons like oils and gasoline don't interact well with water. But if we add OH groups are capable of hydrogen bonding. H2O is capable of hydrogen bonding. So, like dissolves like, this whole molecule here can now interact with water on a hydrogen bonding basis, where before it couldn't because we've added these functional groups to it. Now we're going to be covering a variety of functional groups. You've got a list of these located on Blackboard, which you do want to memorize. You want to be able to recognize these not just by sight or given a structure, but you also want to know the general properties and how to compare them. So what we'll start out with is the alcohol. Sometimes you'll see this referred to as a hydroxyl group. You'll see it a lot in biology because molecules like sugar, which also show up in structures like DNA and RNA, you're going to see sugar rings, and these sugar rings have hydroxyl or alcohol groups that are all over them. Now, think of a Volkswagen Beetle. That's a fairly large vehicle. If we put an arm swimmy that we would put on a child on a Volkswagen Beetle, would that make it float? No. It's because it's too small compared to what it's trying to make float. Now, if we have a very, very large organic molecule with a single OH on it, we've now added the OH functional group to this previously what was an alkane. So now it can hydrogen bond. But most of the molecule is not capable of hydrogen bonding. So this molecule to the right here that I've just drawn, the skeletal structure of, wouldn't mix well with water. But the molecule on the left, the sugar, is large, but it has alcohol groups all over it. So it's going to interact well with water. It's going to be able to hydrogen bond in multiple locations. Now, alcohols, as a functional group, we're going to see show up in alcoholic beverages, hence the name. So wines, fermented beverages, beers, because we see the sugars that are in grains and vegetables and fruits ferment into these alcoholic beverages. They start as the sugars, they end as the alcohols. One of the problems associated with this functional group is binge drinking. Now, we have an enzyme called alcohol dehydrogenase. It's meant to break down the alcohol that's in our body. We start with ethanol. This is the active form of alcohol that's in alcoholic beverages. And it undergoes a process of breaking it down. And it first breaks down into acetaldehyde, which further breaks down into acetic acid, which further breaks down into CO2 and H2O, which are removed from the body. It's fine once we get to this point, but the problem with drinking too much resides in these two central chemicals, acetaldehyde and acetic acid. To give you a feel for why it's a problem, table vinegar is 5% acetic acid. Acids tend to be corrosive. So if you have a buildup of ethanol in your system, what happens is we end up getting a buildup of acetaldehyde, which is related to formaldehyde. That's a preservative, that pungent smell that sometimes you smell coming from biological labs. And acetic acid, which is a corrosive acid, build up in the liver. When you get this buildup, it can cause inflammation, it can cause tissue damage, especially in the instances of binge drinking. Now, before we move on, there's a general way to represent these functional groups, and that's to say R, OH. The functional group itself is this OH piece. The R represents a carbon group, so we could have it hanging off of a straight chain, we could have it hanging off of a ring. The R stands for what it's hanging off of, and the R means it's hanging off of some type of carbon structure. Alright, so if alcohols were ROH, then if we wanted to look at an ether is ROR. It can also be called the ether bunny. We draw on little ears and a nose. We can give them little teeth. We've got ourselves an ether bunny. But the important part is we can trace from one carbon through the oxygen all the way over to the other carbon in one line without having to double back on anything. The oxygen that's in an ether is in the carbon chain, so you can read it across. Now, something important here, if you look at that oxygen, is there an H directly coming off of it? No, I've got a carbon on this side, and I've got a carbon on this side, but no H directly connected to the O. So ethers do not H bond. If you look in the molecule to the left here, I've got a carbon where I'm bolding. We can trace it directly through that oxygen all the way to the carbon on the other side. We have R, O, R. That's what gives us the ether. Now you can see this in any orientation. I could have an ether like this. I could have an ether like this. What matters is I have carbon, oxygen, carbon, all in a line. Now ethers were some of the first anesthetics that we used. There was a problem with ethers though. They're very volatile. Ethers have dipole-dipole forces, which aren't as strong as H bonding. They're relatively volatile, which means that they go into the gas phase pretty readily, and they're very flammable. So using this as an anesthetic in hospitals, it led to issues with hospital fires. So what they ended up doing is taking the original ether used for anesthetics and substituting in Fs and substituting in Cls to make it a heavier molecule. And as molecular weight, or MW, goes up, volatility goes down. This is called halothane. It is the original ether, which has been modified to be a heavier molecule, less flammable, and much less volatile, so much less of a risk in the hospital setting. Now, phenol, you'll recognize by seeing a six-sided ring. This is our next functional group. It will have an OH coming off of it, and it can have an R group coming off in any one of these positions. So, the big thing to look for here is the six-sided ring with alternating double bonds and an OH group coming off of that six-sided ring. So it does have a higher boiling point. It's harder to boil than ethers and alcohols. Now, if we look at this, phenols can H bond. Phenols are going to interact with water because water H bonds and phenol H bonds, and you see a like dissolves like scenario. Molecules with similar intermolecular forces are going to dissolve in one another. So phenol does interact with water because both H bond. If you just looked at the boxed pieces here, this looks like an alcohol. But a general rule for spotting these functional groups is to look what's next to it. And if we place a six-membered ring with double bonds that are alternating with single bonds, so double, single, double, single, double, single, we end up with a phenol. Now, in the acid-base chapter, we memorized 7 strong acids. Phenol was not one of those 7 strong acids. So whenever you come across an acid that wasn't on that strong acid list, it's a weak acid. So phenol does count as a weak acid, and the proton it tends to give away, right here. It's the proton that you could find, or the H that you could find in its alcohol portion. Now, phenol has an interesting history. Phenol is corrosive. Phenol will actually penetrate the skin and kill the pigment producing cells, so it does have a tendency to bleach the skin. But because it's corrosive, it can be used medically. It can be used in treatments of smoothing the skin. Acid peel treatments, when extreme, can make use of phenol facial peels. It was also used as one of the first antiseptics. Now, this was a byproduct of the coal tar that was burned in oil lamps that you would see in street lamps in the 1800s. Phenol was extracted from this coal tar, and it was discovered that it could be used as an antimicrobial agent. It would kill bacteria, it would kill microbes. There are downsides because we said it would bleach the skin. It's also corrosive to the skin, but the upside was you wouldn't die to surgery. That used to be pretty much a death sentence in the 1800s, having to go into surgery. But with the introduction of phenol, it became less of a scare because instrumentation and hospital surfaces and hospital rooms began eventually to be treated for these with these antimicrobial agents such as phenol. Alright, thiol is going to be our next group. We're going to have some form of carbon, either a ring or a straight chain or a branch, attached to SH. Now if it's coming from the other side, we could have this. Either one represents a thiol. The important part to look at is an H directly connected to an S. That's what's going to make a thiol group for us. Now, similar to an alcohol was ROH with some carbon group attached to an O that's directly connected to an H. But when we get to a thiol, we look for a sulfur connected to a hydrogen. They cannot H-bond because H-bonding only occurs if this H were connected to an N, an O, or an F, and we don't have any of the three here. We have sulfur. Now, these are known for having terrible smells. Personal story, when I was back doing research, I worked with a compound. It was called a mercaptan. And a mercaptan, the one that I worked with, was a direct descendant. It's pretty much the active ingredient in skunk spray. Spilling a few millionths of a liter. Picture breaking a 1 liter soda bottle into a million pieces. Just spilling 5 millionths of a liter on my fingertip, I absorbed it through my skin and had a skunk-like odor for about 2 weeks. Wasn't very pleasant. So these thiols are known for being volatile. They're known for having a very recognizable smell to them. But they also have some familiar and good smells as well. While they're pungent, we do use thiols in cooking. Onions and garlic have characteristic thiol smells. If you look at the left versus the right molecule, the only thing that differs is this part here. Garlic has a double bond, whereas onions have a single bond in their place. So closely related molecules, closely related scents, and relatively pleasing to the palate if you're into spicier cooking. Thiols are also related to hair treatments and perms. Cysteine residues in the hair. Hair is partly composed of proteins, and we can see what's called a cysteine group or a thiol group coming off. If I have another thiol coming from the other direction, what can happen is I can bond together these two sulfurs. That results in what's called a cysteine bridge, when I get two thiol groups to form a bridge and bond to one another. Now, when you get a hair perm, you first have to relax the hair. You're breaking the existing bonds and existing bridges in the hair, and we're going back in this direction. You then wrap the hair around curlers, or you retrain the hair to the structure you want it to be in, and then you reform the bonds. You reform these bridges, thus locking the hair in place. And it's a terribly smelly process, partly because we're dealing with thiol-related chemicals. Alright, next functional group is called aldehydes and ketones. They're two functional groups, but they belong to the same family. If you look at the left and the right structure at the bottom here, they're related in that they have a major similarity. If you can spot the similarity, circle it in your notes. Both of these have this piece that I'm circling here. They have a carbon double bound to an oxygen. While this isn't a functional group itself, it's called a carbonyl when you have a carbon double bound to an oxygen. Now what's to either side of that carbonyl is what makes an aldehyde versus a ketone. So if we have a ketone, we'll have R, carbonyl, R, carbons on both sides, like the molecule that we have to the right. If I have at least one hydrogen instead of a carbon to the side of the carbonyl, that's what makes it an aldehyde. So a carbon on either side makes it a ketone. At least one hydrogen to one side of the carbonyl makes it an aldehyde. So, writing these in the form that we'll tend to see them, for aldehydes, we'll have some kind of carbon, which is represented by R, going up to a carbonyl, going down to an H. So you tend to see aldehydes on the ends of molecules. If you look at the molecule to the right here, cinnamaldehyde, aldehyde is the name. This is the common name for this chemical, provides the smell for cinnamon. To spot the aldehyde or ketone in this molecule, look for the carbonyl, and then I've got an H right next to it. So this whole piece here is an aldehyde because I have a carbonyl with a hydrogen on one side. That's what puts the aldehyde in cinnamaldehyde. Now if we jump over to the left molecule, it's called benzaldehyde. So we should be seeing another aldehyde group here. And I've got my C double bond O, my carbonyl, with an H directly attached. So that's making that an aldehyde. Now jumping down to the bottom, I've got carvone. And I'm looking for R attached to a C, double bound to an O, attached to an R. That's what's going to make up our ketone. And if we fill that in on the picture, I've got an R here, an R here, and a C double bound to an O. There's my ketone. So when we look at the solubility of the groups that we've looked at so far, we said there's a general rule that like dissolves like. When we talk about solubility, we talk about it in this class with respect to water. And since like compounds dissolve like compounds, H2O H bonds, because it has an H directly connected to an NO or F in its structure, then things that will be more soluble will be able to H bond. So alcohols, ROH, are capable of H bonding. Aldehydes and ketones can't H bond, but they do have dipoles. So they have a positive side and a negative side. So they do have that going for them because water also has a positive side and a negative side. So alcohols are the most soluble because they can H bond. Aldehydes and ketones are next up in the lineup. Ethers also have a dipole, but not as strong of one. So we're going to show them as the fourth in the list, so even less soluble. But then we get down to alkanes. And alkanes are nonpolar, just by definition. And think back what force that nonpolar molecules had. It was the weakest force of the four. It was dispersion forces. So, in order of solubility, we would say more soluble for the alcohols, down to essentially not soluble for the alkanes. Alright, and boiling points follow the same trend as the trend for solubility. Alcohols have the highest boiling point, all the way down to alkanes have the lowest boiling point. The underlying point here is pretty key. The higher the intermolecular attraction, the higher the boiling point. Boiling point is all about getting liquid molecules that are packed in close together to go to the gas phase. The easier it is to break the interactions between the molecules in the liquid, the easier it is to get these molecules and atoms to go into the gas phase. So if I have something with weak intermolecular forces like an alkane, this process will happen easily. We'll go from the liquid to the gas phase readily, and that's considered volatile. So we would say low boiling points would go with the alkanes that have weak forces. Higher boiling points would be associated with substances that can H bond. Our next functional group is called the aromatic. When you think aromatic, you might think smell. If something is said to be highly aromatic, it has a pungent smell associated with it. Now we've looked at a similar functional group already. It was called phenol. We had a six-sided ring with alternating double bonds and an OH group. If we take away that OH group and just have a six-sided ring with alternating double bonds, we get the structure shown here. This is called benzene. A common way to write this in organic chemistry is to take a shortcut and draw a circle in, which indicates it's an aromatic. Drawing this circle in is equivalent of writing in alternating double bonds throughout the structure. Now, let's see if we can identify some of the functional groups that are in this molecule below. I'll circle them to start out with. Now pause the video and see if you can identify the functional groups that are in this molecule. Alright, we'll label these functional groups as number 1, number 2, number 3. Number 1, I've got a carbonyl group. So the question is it an aldehyde or is it a ketone? Well, I've got a carbonyl with an H on one side. That's going to make this an aldehyde. If it had a carbon on either side of the carbonyl, it would be a ketone. But since I have an H directly to one side, it's called an aldehyde. Number 2, I've got a six-sided double ring, or a six-sided ring with alternating double bonds. And then I've also got an HO coming off of it. That's going to make number 2 a phenol. And finally, number 3 is a carbon directly connected to an oxygen, directly connected to a carbon, and they're all in one line. It's ROR, or if we think back, the Easter Bunny, or the ether bunny, so we would call this an ether functional group. And to answer the question on whether this molecule can hydrogen bond or not, you need to look through the entire molecule to see if there's an H directly connected to an N, an O, or an F. And we have that. OH. The alcohol group is capable of hydrogen bonding. Alright, on to the second half of this lecture. We're going to deal with chirality. Molecules have a property, and organic molecules especially have a property called chirality, which we can relate to things that we see in our everyday lives. Have you ever put your shoes on the wrong foot? How does that feel? Feels a little strange. Your left hand is different from your right hand. The connectivity is all the same. We've got a pinky, an index finger, a middle finger, a pointer finger, and a thumb, all connected to the palm of our hand. But we would say our left hand is distinctly different from our right hand in the sense that they're mirror images of one another. Now, we've talked about isomers before. Isomers have the same formula but different connectivity. Stereoisomers are a different flavor of this idea. They do have identical formulas, but they have identical connectivity. You don't change the way things are arranged. Just like your hands, your fingers and thumb are all connected to your palm on both of your hands. The difference is they're arranged differently in three-dimensional space. Your hands are mirror images of one another, so they would be considered stereoisomers. Your shoes are mirror images of one another, so they would be considered stereoisomers. Same formula, different arrangement in three-dimensional space, but the same connectivity. So, take a look at these shoes. If we drew a little mirror plane going through here, that could be a mirror image. This shoe could be reflecting through the mirror. That's when we get a chiral relationship. Now in molecules, and specifically in organic molecules, you look for two different things. To identify a chiral carbon, which you would look at an entire structure and pick out different carbons that might be chiral. If a molecule has a chiral center, we're going to take it to be a chiral molecule. It's going to have 4 bonds on a chiral carbon, and all 4 bonds have to be to different chemical groups. So let's look at this picture on the bottom left here. This carbon has 4 different groups attached. It has the OH, or an alcohol group, has the Cl, has the H, and it has a CH3. 4 unique groups, so this would be considered chiral. And on the right, if we look at it, we've got a mirror image. The H's are in the back, the OH's are pointing towards one another, the CH's are on the front, so perfect mirror images. Let's see if we can identify a chiral carbon inside carvone. Carvone is the name for the 2 molecules on the left and on the right here. Now they're enantiomers. They're mirror images of one another. We could say this is the left image, this is the right image. Now comparing the two, if we were to find the carbon where they're chiral, we would look for a carbon where 4 different things are attached, and we would look for a carbon with 4 total bonds coming off of it. I'm going to start here at this carbon. This carbon has 1, 2, 3, 4 bonds coming off of it. The H is unique. This is unique. If we keep tracing around to the left, we come into contact with a carbonyl, but if we keep tracing to the right, we come into contact with an alkene. So this carbon that's been indicated has 4 different groups attached. So this would be considered the chiral carbon in this molecule. There are no others to choose from. On the right-handed molecule, or right side molecule, this is our chiral carbon, because again we have 4 different types of groups attached. Even though traveling in both directions we come into contact with a carbon, if you keep going, I've got a carbonyl on one side and an alkene on the other, which makes the 2 sides different. Alright, thank you for being around for Unit 4, Lecture 2. Make sure you check out Unit 4, Lecture 3 and 4, which are coming out soon.